Our understanding of the universe was forged by a handful of silent explosions. This is the story of the 30 astrophysical events that redefined modern cosmology, moments where the cosmos itself offered a clue and changed everything. By the end, you will see the entire history of the universe, from its first whisper to its ultimate fate, woven into a single, startling narrative. We will uncover how a persistent hiss in a radio antenna rewrote our origin story, and why the transition of a star halfway across the visible cosmos forced scientists to invent a mysterious, repulsive force. What do you believe is the most surprising thing the universe has ever shown us? That opening act was a soundless flash of unimaginable energy. For a long time, the very idea of a universe with a beginning was considered philosophical, even theological speculation. The prevailing view was of a static, eternal cosmos, unchanging in its grand design. The shift began not with a bang, but with a subtle, universal drift. Astronomers like Edwin Hubble, peering through the Great Telescope at Mount Wilson, noticed something peculiar about the faint, fuzzy nebulae they were studying. The light from these distant galaxies was stretched. Its color shifted toward the red end of the spectrum. This redshift was a cosmic fingerprint, and its meaning was profound. The galaxies were not just moving, they were racing away from us and from each other. The entire fabric of space itself was stretching, carrying the galaxies along like points on an expanding surface. If the universe is expanding now, then tracing that expansion backward in time logically points to a moment of incredible density and temperature, a singular starting point. This was the theoretical beginning, a brilliant but contested idea. It needed proof, a tangible relic from that primordial state. The proof arrived by accident in the mid-1960s in the form of a persistent, uniform signal. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a sensitive horn antenna in New Jersey, plagued by a gentle hiss that came from every direction in the sky. It was not equipment failure, it was not terrestrial interference, and it famously was not pigeon droppings. They had stumbled upon the cosmic microwave background radiation, the cooled and faded afterglow of the universe's birth, now just a few degrees above absolute zero. This faint whisper was the predicted echo of that first moment, the cooled embers of the initial flash. This discovery transformed our understanding. It gave us the canvas. It established that our universe had a hot, dense beginning roughly 13.8 billion years ago. And from that moment, everything we see, every galaxy, every star, every atom in our bodies was forged. It set the initial conditions, the subtle variations that would, over eons, allow gravity to sculpt the vast cosmic web. This foundational event redefined our origin story from one of static eternity to a dynamic narrative of cosmic evolution, a story that begins with a single, silent flash. And with that canvas stretched and primed, the universe began to paint its first structures with a shadow we cannot see. That gentle hiss echoing across the cosmos was the sound of a scientific revolution. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were not looking for the origin of the universe. They were simply trying to calibrate a massive, horn-shaped antenna for satellite communication. Yet their work was accompanied by an inexplicable, uniform signal that permeated every observation, day and night, in every direction they pointed their instrument. They meticulously checked every connection, they cleared the antenna of debris, but the signal remained. It was not a flaw in their machine, nor was it a transmission from Earth. It was the universe itself speaking in a whisper. This persistent signal was the cosmic microwave background radiation, the cooled and stretched afterglow of the universe's hot, dense infancy. Its discovery was the first direct, tangible evidence for the Big Bang theory, a triumphant confirmation that our cosmos had a definitive beginning. This was far more than just a point on a timeline. The cosmic microwave background is a preserved snapshot of the universe when it was a mere 380,000 years old. Before that moment, the cosmos was a searing, opaque fog of plasma, where light could not travel freely. As it expanded and cooled, atoms finally formed, and the universe became transparent. That first flash of liberated light has been traveling for over 13 billion years, cooled by the expansion of space into the faint microwave glow Penzias and Wilson detected. This early portrait of the cosmos holds immense detail. When we look at it with modern satellites, we do not see a perfectly smooth blanket of radiation. Instead, we see tiny, minute variations in temperature, mere millionths of a degree. These are the cosmic seeds. These faint textures in the fabric of the early universe are the gravitational signatures of denser regions, places where matter had begun to gather under its own influence. Every galaxy, every cluster, every filament in the vast cosmic web we see today grew from those infinitesimal beginnings. The discovery did not just quiet rival theories of a steady-state universe, it handed cosmologists the ultimate calibration tool. By studying the precise patterns in this ancient light, scientists could measure the universe's geometry, determine its age with unprecedented accuracy, and even calculate its fundamental ingredients, like the amount of ordinary matter and dark matter. It transformed cosmology from a field of grand speculation into a precision science, where theories could be tested against solid, observational data. This relic radiation opened a permanent window into the primordial universe, a direct line to our deepest past. But if those tiny textures were the seeds of all structure, a pressing question emerged. What planted them? What process in the earliest moments of creation imprinted those crucial variations onto the smooth canvas of the newborn cosmos? The answer would require a leap even more profound, into a fraction of a second so brief it defies human intuition. The smoothness of that primordial canvas was in fact a profound mystery. If the cosmic microwave background was truly so perfectly uniform, how did the magnificent, clumpy universe we see today ever emerge? For structure to form, there had to be seeds, places where gravity could get a slightly stronger grip. For decades, scientists searched for these seeds within the faint microwave glow, but the signal remained stubbornly smooth, posing a quiet challenge to the entire narrative. The breakthrough came not from the ground but from orbit. In 1992, the team behind the Cosmic Background Explorer satellite, known as COBE, announced a discovery of breathtaking subtlety. They had finally detected the ancient fingerprints. The satellite's exquisite instruments revealed that the cosmic microwave background was not perfectly uniform. It contained minuscule temperature variations, where some patches of the sky were ever so slightly warmer or cooler than others. The difference was almost impossibly small, about 1 part in 100,000. To put that in perspective, if the early universe were as smooth as a sheet of glass, these variations would be like the gentle ripples on the surface of a pond. But in the cosmic context, these ripples were everything. They were the gravitational seeds, the primordial density fluctuations imprinted on the fabric of space-time when the universe was a mere infant. Slightly denser regions marked by subtly warmer spots in the map held a tiny bit more gravitational pull. Over billions of years, that extra pull would attract more and more matter, slowly snowballing into the first stars, the first galaxies, and the vast web-like clusters we observe today. This map was more than data. It was a direct image of the universe's initial conditions, a baby picture showing the raw potential for all future structure. The COBE findings did more than solve the galaxy formation problem. They provided overwhelming, precise evidence for a revolutionary idea called cosmic inflation. This theory proposes that in the first fraction of a second after the beginning, the universe underwent a period of exponential, faster-than-light expansion. This profound stretching would have taken quantum fluctuations, the tiny jitters inherent to empty space at the smallest scales, and magnified them to cosmic proportions. Those microscopic quantum jitters became the macroscopic density ripples that COBE observed. For the first time, a direct link was forged between the bizarre rules governing the subatomic world and the grand architecture of the cosmos. The universe's blueprint had been retrieved. This precise mapping of our ancient sky gave scientists their first detailed look at the ingredients list for the cosmos, hinting at the presence of mysterious components like dark matter that would govern its growth. But to truly read that blueprint, to understand the fate written within it, we would need an even sharper image, one that would reveal a universe behaving in a way no one had anticipated. The blueprint retrieved by COBE held a hidden prediction about destiny. By precisely measuring those ancient ripples, scientists could calculate the total density of the universe, which in turn would reveal its ultimate fate. Would gravity, pulling everything together, eventually slow the expansion to a halt or even reverse it in a great crunch? Or would the universe expand forever, growing ever colder and more diffuse? The answer hinged on a simple measurement of how the expansion rate had changed over cosmic time. To measure this, astronomers needed a special kind of cosmic milepost, a standard candle so brilliant and consistent it could be seen across billions of light years. They found it in the final brilliant moments of certain stars. Type 1, a supernova, are thermonuclear explosions of white dwarf stars. Because they always explode at nearly the same critical mass, they always release almost the same amount of light. This makes them perfect for measuring vast distances. If you know how bright the explosion truly is, and you measure how dim it appears from Earth, you can calculate exactly how far away it happened. More importantly, by looking at supernova from different eras, you can chart how the expansion of the universe has sped up or slowed down over billions of years. In the late 1990s, two independent teams of astronomers embarked on this grand cosmic survey. They pointed the world's most powerful telescopes at the deepest reaches of space, collecting light from these stellar events that occurred when the universe was half its current age. They were fully expecting to see the telltale sign of a universe gradually slowing down, its expansion braked by the collective gravitational pull of all the matter within it. The data they gathered told a radically different story. The distant supernovae were fainter than they should have been, much fainter. This could mean only one astonishing thing. These ancient stars were farther away than the standard model of a slowing expansion predicted. The universe was not expanding at a steady pace, nor was it decelerating. It was accelerating. The fabric of space itself was stretching at a faster and faster rate, pushing galaxies apart with a force that grew stronger over time. This was a result so unexpected that the team spent years checking and rechecking their work, searching for hidden errors in dust absorption or stellar evolution. But the evidence was undeniable. The discovery, announced in 1998, overturned a fundamental pillar of cosmology. Gravity, the force that shapes galaxies and holds planets in orbit, was not the dominant player on the largest cosmic stage. Something else was at work, a mysterious, repulsive force permeating the vacuum of space itself. Scientists called it dark energy. The implications were and remain profound. Dark energy appears to constitute about 68% of the total energy density of the cosmos. It is the dominant component of the universe, yet we have no idea what it is. Its existence forces a complete revision of the standard model of cosmology and suggests a future for the cosmos that is deeply unfamiliar. If dark energy continues to accelerate the expansion indefinitely, the distant future holds what cosmologists call a big freeze. Galaxies will be pushed apart until they are isolated islands, their stars will burn out, and the universe will become an ever-cooling, ever-darkening expanse of emptiness. For revealing this transformative truth, the leaders of the supernova teams were awarded the Nobel Prize in Physics in 2011. The discovery of the accelerating universe stands as one of the most humbling and pivotal events in modern science. It revealed that we understand only about 5% of the universe, the ordinary matter that makes up stars and planets. The rest, 95%, is composed of dark matter and dark energy, two profound mysteries that define the cosmos. This revelation did not come from looking at the ancient past, but from interpreting the brilliant final chapters of stars. And to understand those conclusions, we must first understand the brilliant lives that preceded them, forged in the earliest furnaces of the cosmos. That predictable brilliance is the universe's most reliable milepost. A Type 1, a supernova, is not just any stellar explosion. It is a precision detonation with a very specific origin story. It begins with a white dwarf, the dense, Earth-sized core left behind after a Sun-like star has exhausted its nuclear fuel. This stellar remnant is incredibly stable, held up against its own immense gravity by a quantum mechanical force. But if this white dwarf has a companion star, a cosmic dance of matter and fate begins. Gas from the companion can be pulled across space, slowly accumulating on the surface of the white dwarf. With each passing millennium, the white dwarf grows heavier. It is a slow, steady climb toward a single, critical threshold known as the Chandrasekhar limit. When the white dwarf's mass reaches about 1.4 times that of our Sun, the pressure and temperature in its core become so extreme that carbon fusion ignites almost instantly. This is not a gentle burn, but a runaway thermonuclear event that transforms the entire star in a flash of light so intense it can outshine an entire galaxy. This consistent trigger mechanism is what makes these events so valuable to science, because they all ignite at nearly the same mass. They all release nearly the same amount of intrinsic light. Imagine you are in a vast, dark field, and someone lights a series of identical lanterns at varying distances. The farther away the lantern, the dimmer it appears. By knowing the true brightness of the lantern, you can calculate its distance just by measuring how dim it looks. Type 1, a supernova, are the universe's lanterns. Their predictable luminosity allows astronomers to peer across billions of light years and measure cosmic distances with extraordinary precision. It was this very property that enabled the profound discovery of the accelerating universe by showing that distant stellar events were inexplicably faint, pushed farther away by the stretching of space itself. But their role extends far beyond that of a simple measuring stick. These tremendous transformations are also the universe's primary foundries for iron. In those final, furious moments, nuclear fusion forges elements like nickel, cobalt, and iron in immense quantities. The event then scatters this newly minted material across interstellar space, seeding the galaxy with the raw ingredients for rocky planets and ultimately for life itself. Every iron atom in your blood, every speck of metal in the device you are using right now, was likely forged in the heart of an ancient star and distributed by a stellar event eons ago. So these events perform a dual cosmic duty. They are the precise instruments that map the geometry and fate of the cosmos, and they are the essential recyclers that enrich it with the elements of complexity. Their light guides our measurement of the universe's expansion, but to understand what shapes the universe itself, we must look to a force that casts no light at all. The universe's most reliable mileposts were forged in light, but its true structure is held together by shadow. In the 1970s, astronomer Vera Rubin turned her telescope toward our nearest galactic neighbor, Andromeda, to measure how stars moved within its majestic spiral arms. She expected to find a familiar pattern, one dictated by the laws of gravity and the visible mass of stars and gas. According to Newtonian physics, stars closer to the galactic center, where most of the visible mass resides, should orbit at high speeds. As you look farther out toward the sparse edges of the spiral, the gravitational pull should weaken, and those outer stars should orbit much more slowly, just as Pluto moves more sluggishly around the Sun than Earth does. Rubin's meticulous observations revealed something astonishing. The stars in the outer reaches of Andromeda were not moving slowly at all. They were hurtling around the galactic center at speeds nearly as great as those of the stars near the core. This was like watching the entire solar system, from Mercury to the distant comets, all whizzing around the Sun at the same breakneck velocity. It simply did not make sense. The visible mass of the galaxy was nowhere near sufficient to generate the gravitational grip needed to hold onto these speeding outer stars. According to the math, Andromeda should have been flying apart, its spiral arms flinging stars into the intergalactic void. Yet it remained beautifully intact. The only logical conclusion was both simple and revolutionary. Andromeda, and by extension every spiral galaxy, must be embedded within a massive, invisible halo of something. This something exerted a powerful gravitational pull, but it emitted no light, absorbed no light, and reflected no light. It was completely transparent to every form of electromagnetic radiation we could detect. Vera Rubin had provided the first robust observational evidence for what we now call dark matter. Her work fundamentally shifted our understanding of cosmic composition. It revealed that the glittering stars and glowing gas clouds we see in a galaxy are merely the decorative lights on a vast, unseen structure. The true mass, the gravitational skeleton of the cosmos, is made of a substance we cannot perceive directly. Subsequent studies have shown that this dark matter outweighs all the ordinary matter, the stuff of stars, planets, and us, by a factor of about 5 to 1. Over 80% of the matter in the universe is of this unknown, invisible nature. This discovery transformed cosmology from a science of the visible to a detective story of the unseen. It forced physicists to accept that the universe is primarily built from a material that does not interact with light, a substance that passes through our bodies and our planet every second without a trace. Vera Rubin's careful measurements of starlight did not just chart the motion of stars, they charted the boundaries of our understanding, defining one of the greatest puzzles in modern science. The hunt for this elusive substance would now require looking beyond serene spiral galaxies to the most energetic collisions in the cosmos, where dark matter might finally betray its presence. The invisible scaffolding of dark matter warps the very path of light itself. This prediction, born from Einstein's revolutionary theory of general relativity, states that mass does not simply exert a pull, it actually curves the fabric of space and time around it. A beam of light traveling through this curved geometry does not follow a straight line. It bends like a car following the curve of a road. When a truly massive object, like an entire galaxy cluster, sits between us and a distant source of light, this bending becomes a powerful cosmic phenomenon. We call it gravitational lensing. For decades, it remained a beautiful theoretical idea, a testament to the strange elegance of Einstein's universe. Then, in 1979, astronomers observed a quasar, an intensely bright galactic core that appeared not once but twice in the sky. They had found the twin quasar, the first confirmed example of strong gravitational lensing. A foreground galaxy's immense gravity had bent the quasar's light, creating two separate, identical images for telescopes on Earth. This was the moment lensing transformed from a mathematical curiosity into an indispensable tool for exploring the cosmos. It gave us a way to see the unseeable. Because gravity does not care whether mass glows or not, the lensing effect is caused by the total mass in the foreground, both visible stars and invisible dark matter. By meticulously measuring how the light from a background galaxy is stretched and distorted, astronomers can create a precise map of the gravitational field, and therefore a map of all the mass present. It is like looking at a distant street lamp through the bottom of a wine glass. The warped, shimmering image of the light tells you everything about the shape and thickness of the glass itself. In the cosmic context, strong lensing creates breathtaking visual artifacts like perfect Einstein rings or multiple images of a single galaxy. But more commonly, we see weak lensing, a subtle shearing effect where thousands of background galaxies appear slightly stretched in a coherent direction, pointing toward the hidden mass. By surveying vast patches of sky and analyzing these tiny distortions statistically, cosmologists can chart the large-scale distribution of dark matter across the universe, revealing the vast web-like structure upon which galaxies are hung. This technique has turned massive galaxy clusters into nature's own telescopes. Their gravitational fields magnify the light from incredibly distant, faint galaxies located behind them, allowing us to peer further back in time than ever before, observing some of the first structures to form after the cosmic dawn. Gravitational lensing did more than confirm a century-old theory. It redefined observation. It gave us a direct method to weigh the invisible, to map the shadow universe, and to use the cosmos itself as a lens to see its own deepest history. Yet, for all its power, lensing showed us the static curvature of spacetime by distant masses. To witness the dynamic fabric of the universe in motion, to feel it ripple, we would need to detect a disturbance born from the most profound events imaginable. The universe's fabric is not silent, it sings. For a century, gravitational waves were a beautiful mathematical consequence of Einstein's theory, a prediction so subtle that even he doubted we would ever detect them. These are not waves of light or sound, but ripples in the very fabric of spacetime itself, generated when massive objects accelerate. Picture the surface of a still pond. Now drop two heavy stones into it. The circular waves that spread out from each impact are like gravitational waves, distortions traveling at the speed of light. Their source must be incredibly energetic, requiring the motion of objects with immense gravity, like orbiting neutron stars or colliding black holes. The challenge was that by the time these ripples reached Earth, they would be vanishingly small, stretching and squeezing space by a distance far smaller than the width of a single proton. Detecting this required an instrument of almost impossible sensitivity. That instrument was LIGO, the Laser Interferometer Gravitational Wave Observatory. It does not look like a traditional telescope. It consists of two immense L-shaped facilities in the United States, each with arms 4 kilometers long. Inside these vacuum tubes, laser beams bounce between mirrors, constantly measuring the precise length of each arm. The principle is elegant. A passing gravitational wave would minutely stretch one arm while compressing the other, and then reverse the effect. This tiny wobble, just 1/10,000th the width of a proton, would shift the laser light in a specific, detectable pattern. After decades of upgrades to achieve this staggering sensitivity, LIGO began its first advanced observing run in September 2015. On September 14th, just days after the run started, both facilities, separated by 3,000 kilometers, recorded an identical signal. It was a brief chirp, a rising frequency that lasted only 0.2 of a second. The data was analyzed, checked, and rechecked. The conclusion was undeniable. LIGO had detected the final moments of two black holes, one about 36 times the mass of the Sun, the other 29, spiraling toward each other over 1 billion light-years away. In a fraction of a second, they merged into a single, more massive black hole, converting an amount of mass roughly 3 times that of our Sun directly into pure energy in the form of gravitational waves. That energy, rippling outward, was the faint chirp that reached Earth. The importance of this discovery cannot be overstated. It was a direct confirmation of a key prediction of general relativity, proving that spacetime itself could be dynamically warped and that these ripples travel at the speed of light. More profoundly, it inaugurated an entirely new field of astronomy. For all of human history, we have studied the cosmos by collecting light from radio waves to gamma rays. Now we had gained a new sense. We could hear the universe. Gravitational waves carry information that light cannot. They allow us to probe the most extreme gravitational environments, like the event horizons of merging black holes, places forever hidden from traditional telescopes. This first detection alone proved that binary black hole systems exist and can merge, solving an open astrophysical question. It was the birth of multi-messenger astronomy, where we can now combine what we see with what we hear to gain a complete picture of cosmic events. That first faint chirp was not an ending but an opening note. It signaled our newfound ability to listen to the symphony of the cosmos, to study its most energetic dances directly. And as our listening skills improved, we would soon hear a collision that would not just ripple space-time, but also paint the sky with light, finally revealing the secret origin of the universe's heaviest elements. That first faint chirp was a promise of a new way to listen, and the cosmos wasted no time in delivering a full symphony. On August 17, 2017, the LIGO and Virgo gravitational wave detectors registered a signal unlike any before. It was not the brief, deep thrum of colliding black holes. This was a longer, rising tone lasting about 100 seconds, the signature of two objects far less massive but incredibly dense spiraling together. Just 1.7 seconds later, orbiting gamma-ray telescopes detected a short, powerful burst of high-energy light from the same patch of sky. The alert went out to observatories across the globe and in space. For the first time in history, astronomers had both heard and seen the same profound cosmic event unfold. The source was a pair of neutron stars, the incredibly dense, city-sized cores left behind by ancient stars, coming together in a galaxy called NGC 4993, about 130 million light-years away. What followed was an unprecedented global campaign. Telescopes of every kind, from radio dishes to the Hubble Space Telescope, swiveled to watch. They witnessed the brilliant aftermath, an event known as a kilonova. This was not the blinding flash of a supernova, but a shorter-lived, intensely hot glow rich with newly forged elements. The observations solved a cosmic mystery that had lingered for decades. We knew light elements like hydrogen and helium were forged in the Big Bang. Heavier elements up to iron were cooked in the hearts of stars and scattered in supernova. But the origin of the very heaviest elements like gold, platinum, and uranium remained unknown. The data from this kilonova was definitive. Spectra from the event showed clear fingerprints of these heavy elements being created in staggering quantities. In that single convergence, an amount of gold many times the mass of our entire planet was synthesized and cast into space. This confirmed that neutron star mergers are the universe's primary foundries for the elements that make up our most precious metals and our most potent nuclear fuels. Every piece of gold jewelry, every platinum catalyst, carries within it the echo of a transformative event from a distant galaxy. But the scientific harvest did not stop there. By combining the gravitational wave signal, which told us the intrinsic strength of the event, with the observed light, which told us its distance, astronomers performed a direct, independent measurement of the Hubble constant, the rate of the universe's expansion. This was a crucial cross-check on other methods, helping to refine our understanding of cosmic acceleration. Furthermore, the extreme conditions of the merger provided a unique natural laboratory to study matter at densities beyond anything we can replicate on Earth, testing the very limits of nuclear physics. This multi-messenger event was a watershed moment, proving that by combining our senses, we can understand the cosmos with a clarity once thought impossible. It connected the physics of gravity, nuclear chemistry, and cosmic expansion into a single, coherent story. Having now witnessed the spectacular origins of the heaviest elements, our journey turns toward the most intense and powerful forces in the universe, where the nature of reality itself is pushed to its absolute limit. The brilliant glow of a kilonova fades, but the most luminous objects in the universe have burned for billions of years. In the early 1960s, astronomers pinpointed star-like radio sources with baffling properties. They were called quasi-stellar radio sources, or quasars. They appeared as faint blue stars, but their light held a secret. The spectral lines were dramatically shifted toward the red, meaning these objects were not stars in our galaxy. They were staggeringly distant, receding with the expansion of the universe. To be visible across such cosmic gulfs, they had to be emitting almost unimaginable amounts of energy, outshining entire galaxies from a region no larger than our solar system. What physical process could possibly power such a tiny, brilliant beacon? The only conceivable engine was gravity itself, harnessed in its most extreme form. The answer was a supermassive black hole. Theorists realized that if a black hole weighing millions or even billions of suns sat at the core of a galaxy, and vast quantities of gas and dust spiraled into it, the resulting accretion disk would heat to incredible temperatures through friction and gravitational compression. This process, converting matter into radiation with extraordinary efficiency, could easily explain the quasar's phenomenal output. This discovery transformed our view of black holes from theoretical oddities into central players in cosmic evolution. We came to understand that quasars are just the active, youthful phase of a galactic core, a brilliant flare marking a period of intense activity. As the available material dwindles, the active nucleus quiets, leaving behind a dormant supermassive black hole. The implications of this are profound. Nearly every large galaxy, including our own Milky Way with its quiet central black hole Sagittarius, a star, hosts such a behemoth. Their presence is not a cosmic accident, it is a rule. Even more astonishing, the mass of this central black hole is closely correlated with the properties of its host galaxy's central bulge of stars. This tight relationship suggests a co-evolution, a cosmic feedback loop. The black hole is not a passive occupant, it is a regulatory engine. During its active quasar phase, the colossal energy released can drive powerful winds and jets of particles at near light speed. These outflows can heat surrounding gas or disperse it, influencing star formation. In this way, the black hole acts as a governor, shaping the growth of its own galactic home. These cosmic powerhouses demonstrate that black holes are integral architects of the cosmic ecosystem, shaping the galaxies they reside in from the inside out. Their immense gravity can influence stellar orbits in dramatic ways, and their magnetic fields can launch jets that stretch for thousands of light years, illuminating the intergalactic medium. They are the silent hearts around which galaxies spin, their growth histories written in the light of ancient quasars. And just as stellar mass black holes can spiral together, these supermassive giants too must meet, their mergers sending the deepest possible tremors through spacetime, a bass note in the gravitational wave symphony we are only beginning to hear. Quiet hearts of galaxies hold stories of ancient brilliance, but to witness the full narrative of cosmic construction, we needed a deeper look. In December 1995, astronomers made an audacious decision. They pointed the Hubble Space Telescope, then the most powerful eye in orbit, at a tiny, seemingly empty patch of sky near the Big Dipper. This area, about the size of a grain of sand held at arm's length, was chosen specifically because it appeared dark, devoid of any nearby stars or known galaxies. For 10 consecutive days, across 342 orbits of the Earth, Hubble's camera collected every single photon of light that arrived from that void. The result was not a confirmation of emptiness, but a revelation of breathtaking depth. The Hubble Deep Field image unveiled a universe thronging with galaxies. Thousands of them, each a faint smudge of light, filled the frame. This was not a simple photograph, it was a core sample drilled straight back through cosmic time. Every galaxy in that image existed at a different distance, meaning its light had traveled for a different length of time to reach us. Some of the faintest, reddest smudges were galaxies seen as they were when the universe was less than 1 billion years old. The image was a direct visual timeline, a gallery of galactic childhood portraits arranged by age. What it showed was transformative. In the early universe, galaxies were not the majestic, well-ordered spirals and ellipticals we see nearby. They were smaller, more chaotic, and far more numerous. They were irregular blobs, often caught in the act of colliding and merging, building themselves up through a dynamic and ongoing process of assembly. The Hubble Deep Field provided the first clear, visual evidence of cosmic evolution, the idea that galaxies themselves changed dramatically over billions of years. The public impact was immediate and profound. That single image, a tapestry of ancient light, communicated the sheer scale and richness of the cosmos with a visceral power no graph or equation ever could. It transformed a patch of apparent nothingness into a window filled with 3,000 galaxies, each containing billions of stars. It humbly redefined our place, showing that even the emptiest corner of our sky was, in truth, a crowded metropolis of cosmic history. Scientifically, it was a data goldmine that fueled entire fields of study. Astronomers could now statistically analyze galaxy shapes, sizes, colors, and distributions across cosmic time. They could track the rate of star formation throughout the universe's history, observing when it peaked and how it has changed. It pushed the frontier of observation back toward the cosmic dawn itself, raising an urgent new question. If we could see galaxies from the universe's first billion years, could we push even further to witness the very moment the first stars ignited, ending the cosmic dark ages and flooding the universe with its first light? The Hubble Deep Field was a glimpse into cosmic childhood, but the universe's infancy remained shrouded in a primordial haze. To see those first steps, we needed an eye that could perceive the heat glow of the earliest objects, light stretched by cosmic expansion into the infrared. That eye is the James Webb Space Telescope. In July 2022, one of its first targets was a region of sky called SMACS 0723, a massive galaxy cluster whose gravity acts as a natural magnifying lens. The resulting image, Webb's first deep field, was not merely a deeper version of Hubble's iconic view. It was a portal to a previously unseen era. Webb's infrared instruments pierced through the cosmic dust and captured the light of galaxies as they existed just a few 100 million years after the Big Bang. What it revealed was both beautiful and bewildering. These infant galaxies, seen during the universe's first few percent of its current age, were not the faint, chaotic blobs many models had predicted. They appeared unexpectedly bright, massive, and already displaying disk and spiral structures. It was as if we opened a family album expecting to see blurry baby pictures, and instead found detailed portraits of toddlers who had already learned to walk and talk with startling speed. This discovery is actively challenging our theories of early galaxy assembly. How could such well-defined structures form so quickly after the universe's birth? The pristine gas clouds of the early cosmos were thought to collapse slowly under gravity's gentle tug, but Webb's data suggests the process was far more efficient and rapid. It hints that the first generation of stars, known as Population 3 stars, may have been unimaginably massive and brilliant, living fast and concluding their cycles in spectacular events that seeded their surroundings with heavy elements much earlier than anticipated. Furthermore, it raises the possibility that supermassive black holes were already forming and influencing their surroundings in these nascent galaxies, providing an additional source of energy and turbulence. Webb is doing more than taking pretty pictures. It is chronicling the era of reionization. This was the pivotal period when the first stars and galaxies switched on, and their intense ultraviolet radiation began to burn away the thick fog of neutral hydrogen that filled intergalactic space, making the universe transparent to light for the first time. By studying the spectra of these incredibly distant galaxies, Webb can detect the specific signatures of this process, watching as the cosmic fog clears in real time across the universe. Each deep field is a core sample into this transformative epoch, showing us not just the actors, but the changing stage upon which all later cosmic history would play out. This new window is forcing a profound rewrite of the cosmic dawn narrative. Structure and complexity emerged with a swiftness we are only beginning to comprehend, suggesting that the seeds planted by inflation grew into mighty trees far sooner than our garden variety models allowed. As we push our vision to the very first light, we must also widen our gaze to appreciate the colossal architecture these infant galaxies would eventually call home, the largest structures ever glimpsed in the observable universe. The infant galaxies glimpsed by Webb were not isolated islands, but the first sparks along a hidden blueprint of unimaginable scale. For decades, our view of the universe was like standing in a forest and seeing only the nearest trees. We knew galaxies existed, we studied them individually, but their grand arrangement across the cosmos remained a mystery. That changed with ambitious, systematic surveys that aimed to map the sky not in pictures, but in 3 dimensions. The most transformative of these was the Sloan Digital Sky Survey. Beginning in the year 2000, it used a dedicated telescope to systematically catalog the positions and distances of millions of galaxies. When those millions of points were plotted, a breathtaking pattern emerged. Galaxies were not scattered randomly like stars in the night sky. Instead, they traced out a vast, intricate architecture, a cosmic web. This web consists of immense filaments, great rivers of galaxies millions of light-years long, connecting at dense nodes where massive galaxy clusters reside. Between these luminous strands stretch unimaginably vast cosmic voids, regions of near emptiness that can span hundreds of millions of light-years. This is the large-scale structure of the observable universe, a pattern so grand it defies human intuition. This web is the direct result of gravity's patient work over 13.8 billion years. It is the grown-up version of the tiny temperature ripples in the cosmic microwave background. Those subtle density variations were the seeds. Over eons, gravity amplified them, pulling dark matter and gas into the denser regions. The dark matter formed an invisible skeleton first, and ordinary matter, the gas that would become galaxies, flowed along that gravitational scaffolding, condensing at the intersections and along the filaments. Mapping this structure has been one of cosmology's greatest successes. By measuring the exact scale and clustering of the web, scientists can perform critical tests of our entire model of the universe. The size of the voids, the thickness of the filaments, the spacing between clusters, all of these details act as a cosmic fingerprint. They tell us the precise amounts of dark matter and dark energy, and they confirm the nature of the initial fluctuations planted by inflation. The cosmic web proves the universe is organized, not chaotic. It shows that galaxies are like lights on a highway system, tracing the underlying dark matter roads we cannot see. Understanding this architecture is essential for explaining everything about cosmic evolution. It tells us how matter flows from voids into filaments and then into clusters, a process that fuels the growth of supermassive black holes and drives star formation rates. It frames the environment for every astrophysical event we study. A supernova in a dense cluster has a different context than one in a more isolated filament. The coming together of galaxies is a direct consequence of this web-like structure, as gravitational interactions within filaments draw them near. This vast skeleton is the stage upon which the entire cosmic story plays out, from the quiet drift of isolated galaxies to the most energetic events at its crowded intersections. Seeing this web transforms our perspective, revealing a universe of breathtaking order woven from the fabric of gravity and time. The cosmic web is a structure of breathtaking order, but its nodes sometimes erupt in bursts of pure energy. In the late 1960s, a fleet of American military satellites named Vera quietly orbited Earth, their sole purpose to monitor for the telltale gamma-ray signature of nuclear weapons tests in space. They were watching for the flash of human conflict, but instead they found a message from the cosmos. These sensitive instruments began picking up brief, intense bursts of gamma radiation, the most energetic form of light, coming not from Earth but from random directions in deep space. The data was classified for years, its meaning a profound puzzle. When the discovery was finally declassified in 1973, it presented astronomers with an enigma. These gamma-ray bursts, or GRB, were incredibly powerful, yet lasted only from milliseconds to a few minutes. They appeared and vanished without a trace, leaving no visible afterglow to pinpoint their origin. For decades, they were one of astrophysics' greatest mysteries. Where could such concentrated energy possibly come from? The breakthrough came with new technology. In the 1990s, satellites like Betelgeuse were finally able to locate these fleeting bursts quickly, and with enough precision to alert ground-based telescopes. For the first time, astronomers could swivel their instruments to the right patch of sky and catch the fading afterglow in visible light, radio waves, and X-rays. This allowed them to pinpoint the host galaxies of these events, revealing their staggering distances. A GRB was not a local phenomenon. It was a cataclysm occurring billions of light-years away. To be visible across such a cosmic gulf, the explosion had to be almost unimaginably powerful, releasing more energy in 10 seconds than our Sun will emit over its entire 10 billion-year lifetime. With precise locations in hand, patterns emerged. Scientists discovered there are two distinct families of gamma-ray bursts. The long-duration bursts, lasting more than 2 seconds, were consistently found in regions of active star formation within distant galaxies. This crucial clue linked them to the final moments of the most massive stars imaginable. Theorists realized these were hypernova, a supernova on a colossal scale. When a rapidly spinning star many times heavier than our Sun reaches the end of its life, its core does not just collapse into a neutron star, it implodes directly into a black hole. The infalling material forms a swirling disk, and powerful magnetic fields funnel twin jets of particles and radiation away from the poles at nearly the speed of light. If one of those ultra-relativistic jets is pointed directly at Earth, we see the blinding, focused beam as a long gamma-ray burst, a profound cosmic signal. The short-duration bursts, lasting less than 2 seconds, were traced to older, more evolved galaxies and often to regions with little ongoing star formation. Their origin was finally confirmed by the landmark gravitational wave detection in 2017. These are the mergers of neutron stars, the same events that produce kilonovae and forge heavy elements. The incredible convergence of two ultra-dense objects also launches relativistic jets, creating the short, sharp flash of a GRB. These events are more than just cosmic fireworks. They are the universe's ultimate lighthouses. Their extraordinary brightness allows us to probe the most distant reaches of space and time, illuminating the gas in the early universe and providing a glimpse into the era of the first stars. They serve as natural laboratories for studying physics at its most extreme, where magnetic fields are immeasurably strong and matter moves at a fraction of light speed. The identification of gamma-ray bursts unveiled a cosmos of sudden, transformative energy, reminding us that the quiet universe we see with our eyes is merely the calm between brilliant, creative storms. While these titanic events reshape the distant cosmos, a quieter, more common kind of stellar conclusion occurs in our own galactic neighborhood, one that laid the very groundwork for our existence. The brilliant jets of gamma-ray bursts are the final focused signals of the most massive stars, but a quieter, more common stellar conclusion has been shaping our galaxy for eons. When a star more than about 8 times the mass of our Sun reaches the end of its life, it does not fade quietly. Its story concludes in one of the most transformative events in the cosmos, a core collapse supernova. For millions of years, the star has been a cosmic furnace, fusing lighter elements into heavier ones in its layered core, from hydrogen to helium, carbon to oxygen, and finally to iron. Iron is a turning point. Fusing iron does not release energy, it consumes it. So when an iron core builds up, the star's central engine suddenly shuts off. Without the outward pressure from fusion to counterbalance the immense inward pull of gravity, the core collapses catastrophically in less than a second. The outer layers of the star, now unsupported, come rushing down, only to rebound off the newly formed ultra-dense core in a titanic shockwave. This rebound blasts the star's entire outer shell into space in a spectacular display that can for a few weeks outshine its entire host galaxy. This is not merely a conclusion, it is the universe's most essential recycling process. All the heavy elements forged during the star's life, and in the extreme conditions of the explosion itself, elements like oxygen, silicon, calcium, and iron, are now scattered into the surrounding interstellar medium. This enriched gas becomes the raw material for the next generation of stars, planets, and ultimately life. Every atom of oxygen you breathe, every piece of silicon in the rocks beneath your feet, was once forged in the heart of a massive star and distributed by such an event. These supernovae are the primary drivers of chemical evolution in galaxies, gradually transforming the pristine hydrogen and helium from the Big Bang into the rich elemental diversity we see today. Humanity has witnessed these cosmic beacons throughout history. In the year 1054, Chinese astronomers recorded a guest star in the constellation Taurus so bright it was visible in daylight for 23 days. That event created the beautiful expanding cloud of debris we now call the Crab Nebula, with a rapidly spinning neutron star or pulsar at its heart. In more modern times, the supernova known as 1987 in the nearby Large Magellanic Cloud provided a front-row seat to a stellar transition. It was the closest observed supernova in centuries, and it delivered a scientific gift of immense value. Hours before the light from the explosion reached Earth underground detectors in Japan, and the United States registered a brief faint pulse of nearly massless particles called neutrinos. This was the direct signal from the collapsing core itself, a burst of ghostly particles that escaped the stellar structure unimpeded. That detection confirmed the theoretical models of core collapse and marked the true birth of neutrino astronomy, proving we could use these elusive particles to peer inside the most energetic events. The legacy of a core collapse supernova is twofold. First, it seeds the galaxy with the ingredients for rocky worlds and biology. Second, it leaves behind a compact remnant, a monument to the star's original mass. For less massive progenitors, the core becomes a city-sized neutron star, an object so dense a single teaspoon of its material would weigh billions of tons. For the most massive stars, the collapse continues unabated, leaving behind a gravitational pit from which not even light can escape, a black hole. These stellar remnants scattered throughout the galaxy are the potential players in future gravitational wave events. They are the endpoints of stellar evolution and the starting points for new kinds of cosmic dynamics. As we trace the flow of elements from these explosions, we begin to see our own solar system, not as an isolated island, but as a direct product of this ongoing galactic cycle of creation, dispersal, and renewal. Our solar system is a product of that ancient stellar recycling, a single family born from the enriched material of countless stars. As we began to explore this local cosmic neighborhood with robotic probes, we expected the laws of physics as we knew them to hold with perfect predictability. Yet even in our own backyard, the universe whispered a faint, puzzling signal. In the late 1980s, scientists meticulously tracking the paths of the Pioneer 10 and 11 spacecraft, then speeding toward the outer solar system, noticed something strange. The probes were ever so slightly off course. They were experiencing a tiny, unexplained deceleration toward the Sun, a deviation so small it amounted to less than a billionth of the acceleration we feel from Earth's gravity. This was the Pioneer Anomaly. The discrepancy was minute, but in the precise world of celestial mechanics, it was a glaring question. Could it be a hint of new physics? Perhaps a modification to Einstein's theory of gravity at very large scales, or an unseen halo of dark matter surrounding our solar system. The scientific community engaged in a decades-long investigation, a testament to the rigor of modern science. Every conceivable explanation was examined, from the influence of the solar wind to the gravitational pull of the Kuiper belt. The ultimate answer was both humbling and illuminating. The anomaly was not a crack in the foundations of physics, but a subtle thermal effect. The spacecraft, powered by radioactive plutonium, were emitting a faint, uneven heat radiation from their electronics and power sources. This tiny, directional push of photons acted like a gentle, constant brake, explaining the deceleration perfectly. While the Pioneer Anomaly did not rewrite the laws of the universe, its legacy is profound. It demonstrated the astonishing precision of our tracking capabilities, allowing us to measure forces smaller than a mosquito's weight acting on a distant object billions of miles away. More importantly, it showcased the scientific method in its purest form. A faint signal in the data sparked global curiosity and rigorous scrutiny, driving researchers to consider and ultimately rule out extraordinary possibilities. This mindset, this willingness to chase the faintest whisper of a discrepancy, is exactly what we need to solve the greater cosmic mysteries of dark matter and dark energy. Those phenomena too appear as subtle anomalies, as gravitational pulls and repulsions we cannot yet see. The Pioneer and Voyager probes taught us to measure with extreme care and to listen intently, for the next paradigm-shifting clue could be hidden in the quietest of signals. As our vision extends from our solar system to the galaxy at large, we find that our cosmic home is not a serene island, but a dynamic structure still shaped by ancient, formative encounters. The quiet lessons from Pioneer were echoed by a more fleeting cosmic mystery. As spacecraft like Galileo, Near, and Rosetta performed precise gravitational slingshots around Earth, engineers noticed another tiny, persistent discrepancy in their speed. After whipping past our planet to gain a boost toward their distant targets, these probes emerged with a velocity ever so slightly different than predicted. This was the Fly-By Anomaly, a whisper of extra acceleration or deceleration on the order of millimeters per second, a deviation smaller than the crawl of a common garden snail. For years, this consistent signal across multiple missions suggested an unseen influence. Was it an unaccounted-for drag from Earth's extended atmosphere at high altitude? Could it be a subtle effect from our planet's rotation warping spacetime, a phenomenon known as frame dragging, imparted to the passing spacecraft? Or did it point to a flaw in our understanding of gravity itself during these complex, high-speed maneuvers? The scientific pursuit to explain it was a masterclass in precision. Researchers dove into increasingly sophisticated models, factoring in the pressure of solar radiation, the thermal radiation from the spacecraft itself, and even the minute gravitational tugs from ocean tides and atmospheric mass. In time, the most likely culprit emerged not from new physics, but from an exquisite refinement of the old. The anomaly appeared to be largely explained by an intricate combination of these subtle conventional effects, particularly the way a spacecraft's own heat radiation interacts with its motion during the flyby. Like the Pioneer Anomaly, this mystery was ultimately resolved by looking closer, not by rewriting the textbooks, yet its legacy is profound. It underscored that in the domain of high-precision astrodynamics, where a millimeter-per-second error can mean missing a distant world by thousands of miles. There is no room for approximation. Every whisper of force, however faint, must be heard and understood. This relentless pursuit of accuracy here on our cosmic doorstep is a direct parallel to the greatest challenge in modern cosmology, the Hubble Tension. Just as we must account for every subtle thermal photon to track a spacecraft, cosmologists must account for every stellar variable and galactic distance to measure how fast the universe is expanding. Today, our two most precise methods for measuring this expansion rate, one using the cosmic microwave background and the other using nearby supernova and stars, yield stubbornly different answers. The discrepancy is small, just a few percent, but like the Fly-By Anomaly, it is persistent. This tension suggests that perhaps our standard model of the universe, for all its success, is missing a subtle ingredient. It could be a property of dark energy that changes over time, a new type of neutrino, or something entirely unforeseen. Solving the great cosmic puzzles demands the same meticulous rigor we applied to understanding a spacecraft's path. By learning to account for every whisper of influence within our own solar system, we train ourselves to hear the faintest signals from the edge of everything, where the next revolution in understanding may be hiding in a discrepancy no larger than a breath. The whisper of a discrepancy has grown into a persistent, unsettling hum. In cosmology, the most profound revolutions often begin not with a bang, but with a number that refuses to agree. Today, that number is the Hubble constant, the rate at which our universe expands. We have two supremely precise, yet completely independent, ways to measure it. The first method looks nearby, using cosmic lighthouses like Cepheid variable stars, and Type 1, a supernova, to chart distances and velocities in our galactic neighborhood. This is like using a finely calibrated tape measure to check the growth of a sapling in your own backyard. The second method looks back to the universe's earliest moments, analyzing the subtle patterns in the cosmic microwave background from the Planck satellite. This is like examining the preserved imprint of a seedling to predict how tall the ancient tree should be today. These two methods, built on decades of painstaking work, should converge on a single, definitive number. They do not. The local measurement suggests an expansion rate of about 73 kilometers per second per megaparsec. The early universe measurement suggests a slower rate, around 67. A difference of a few percent may sound minor, but in the world of precision cosmology, where error bars have been squeezed to remarkable tightness, this gap is a yawning chasm. It is not a statistical fluke. It is a stubborn tension that has survived over a decade of reanalysis and improved data. This is the Hubble tension, and it represents a quiet but profound challenge at the heart of modern cosmology. What it suggests is deeply thought-provoking. Either there is a subtle, unaccounted-for error in one of our most trusted measurement techniques, which seems increasingly unlikely, or our standard model of the universe, the lambda-cold dark matter model, is incomplete. This model, which beautifully explains the cosmic web, the abundance of light elements, and the afterglow of the Big Bang, might be missing a crucial ingredient. Theorists are now exploring extraordinary possibilities. Could dark energy, the mysterious force driving cosmic acceleration, be evolving over time, growing stronger or weaker in a way we have not anticipated? Could there be a new, previously unknown type of neutrino or other exotic particle subtly altering the expansion history? Or does the discrepancy point to something fundamental about the nature of gravity itself, requiring a tweak to Einstein's equations on the largest scales? This tension is not a failure of science. It is science in its most vital and exciting form. It exemplifies the relentless process of questioning and refinement. When two impeccable lines of evidence point in different directions, it forces a profound re-examination of our foundational assumptions. Entire new observational campaigns, like those using gravitational waves as standard sirens, are now underway to provide a third, independent check. The Hubble Tension is a gravitational pull on the collective mind of cosmology, drawing us toward a potential revolution. It reminds us that our understanding of the cosmos is not a finished book, but a living story, and the next chapter may require us to revisit the very first moments where our current narrative of cosmic inflation began. That persistent tension in our cosmic measurements forces us to look back to the very beginning, to the mechanism that set the entire stage. The universe we observe is remarkably uniform and flat on the largest scales, two facts the classic Big Bang model struggled to explain. How could regions of space now billions of light-years apart, which could never have been in thermal contact, share the exact same temperature? Why does the geometry of our cosmos appear so perfectly balanced between eternal expansion and eventual collapse? In the early 1980s, physicist Alan Guth proposed a radical and elegant solution, a single idea that would reshape our origin story. He called it cosmic inflation. This theory suggests that in the first incomprehensibly tiny fraction of a second after the beginning, the universe underwent a period of exponential, faster-than-light expansion. Space itself ballooned by an unimaginable factor in a span of time perhaps as brief as 10 to the negative 32 seconds. This profound stretching smoothed out any initial wrinkles, explaining the stunning uniformity we see in the cosmic microwave background. It also flattened the geometry of the observable universe, just as inflating a balloon makes any small patch on its surface appear flatter and flatter. But inflation's most profound gift was the creation of structure from nearly nothing. In the seething quantum foam of that primordial instant, tiny fluctuations in energy were inevitable. The rapid expansion of inflation took these microscopic quantum jitters and stretched them to macroscopic proportions, imprinting them into the fabric of spacetime as slight differences in density. These are the primordial seeds, the very same minute temperature variations first mapped by the COBE satellite. Every galaxy, every cluster, every filament in the cosmic web grew from these quantum ripples magnified to cosmic scales. In this way, inflation provides a direct, breathtaking link between the bizarre rules governing the smallest particles and the grandest structures in the cosmos. While we lack direct, definitive evidence for inflation, its predictions have been spectacularly confirmed. It predicted a universe with a flat geometry, which our best measurements of the cosmic microwave background confirm with incredible precision. It predicted the specific statistical pattern of hot and cold spots in that ancient light, a pattern that matches observations exactly. It predicted a nearly scale invariant spectrum of density fluctuations, meaning the ripples should look statistically similar on all sizes, which is precisely what we see in the distribution of galaxies. This theoretical event redefined the narrative of our first moments, suggesting an engine of expansion driven by a mysterious field whose energy temporarily dominated the cosmos, a mechanism far more powerful than anything described by our standard particle physics. The quest to prove it definitively continues, focusing on a specific signature it should have left behind. Theorists predict that the rapid expansion of inflation would have generated a background of primordial gravitational waves, ripples in spacetime from the birth of the universe itself. These waves would have left a distinct, swirling pattern in the polarization of the cosmic microwave background, a faint fingerprint known as B modes. Detecting this signal is one of the great quests of modern cosmology, for it would connect the gravitational ripples we now hear from black hole mergers to the very first tremors of creation. It would be a direct line from the quiet hum of our detectors today to that transformative instant when our entire observable universe was smaller than a single atom. Even our most familiar celestial landmarks can suddenly behave in strange and unexpected ways. In late 2019, the brilliant red supergiant star Betelgeuse, the left shoulder of the constellation Orion began to fade. This was not a subtle shift but a dramatic dimming visible to the naked eye. By February 2020, its brightness had dropped to about a third of its usual luminosity, a change so profound it sparked global speculation. Betelgeuse is a massive star on the brink of its final act, a prime candidate in our galactic neighborhood to conclude its life in a spectacular core collapse supernova. For a thrilling few months, the world wondered if we were about to witness that historic event firsthand. Astronomers mobilized a global network of telescopes, from the Hubble Space Telescope to sophisticated ground-based observatories, to scrutinize the star in unprecedented detail. The data they collected told a fascinating story, one of stellar drama rather than stellar demise. High-resolution images and spectral analysis revealed the likely culprit. Betelgeuse, in its turbulent late stage of life, had likely ejected an immense cloud of superheated gas from its surface. As this material drifted away from the star, it cooled and condensed into a vast shroud of dust, partially obscuring Betelgeuse's southern hemisphere from our view. It was as if the star had coughed out a cosmic veil, temporarily dimming its own light. While it was not the supernova many had anticipated, the great dimming was a scientific gift. It provided a real-time, close-up view of the processes that govern a massive star's final chapters. Red supergiants like Betelgeuse are known to be unstable, pulsating in size and shedding colossal amounts of material into space. This event showed that mechanism in dramatic action, illustrating how these stars lose mass and seed their surroundings with the heavy elements and dust that will form future stars and planets. The detailed observations allowed scientists to study the dynamics of stellar surface activity and mass loss with a clarity never before possible for such a distant star. This episode highlighted a crucial truth about the cosmos. The universe is not a static painting, but a living, changing system. Even stars that have guided humanity for millennia are active participants in a cycle of creation and transformation. Betelgeuse's dimming demonstrated the power of our modern, interconnected observational web, capable of monitoring these changes almost as they happen and transforming public curiosity into profound scientific insight. It served as a captivating rehearsal, a reminder to keep our eyes on the sky, for the day when Betelgeuse or another nearby giant does finally erupt will be a transformative moment for all of humanity, a chance to witness cosmic history in the making. The processes that shape a single star's fate are the same forces that, on a galactic scale, dictate the rhythm of creation across the universe. The processes shaping a single star are the same forces that launch cosmic messengers across the galaxy. In October 2017, a faint point of light moving at unprecedented speed was detected by the Pan-STARRS telescope in Hawaii. It was not bound by the Sun's gravity. This was our first confirmed interstellar visitor, an object from another star system passing through our own. Named Oumuamua, a Hawaiian term for scout, it presented astronomers with an immediate and profound puzzle. Its trajectory was hyperbolic, meaning it was just passing through, but its light curve revealed something even more startling. The object's brightness varied dramatically as it tumbled, suggesting an extreme, elongated shape, perhaps 10 times longer than it was wide. No asteroid or comet in our solar system looks quite like that. Then came the real mystery. As Oumuamua sped away from the Sun, its path showed a slight but clear deviation from what gravity alone would dictate. It was experiencing a tiny, non-gravitational acceleration. For a comet, such a push is common, caused by outgassing as sunlight vaporizes ice, forming a visible tail. But Oumuamua showed no coma, no tail, no detectable gases at all. This absence of visible activity around such an oddly shaped object fueled intense scientific debate. Explanations ranged from the exotic to the extraordinary. Perhaps it was a fractal dust aggregate, a loose collection of material with a very low density. Perhaps it was a shard of a Pluto-like world shattered by a distant impact, or, as some speculated, could its acceleration be explained by the subtle pressure of sunlight itself, if the object were extremely thin and light, like a solar sail of natural origin? While most scientists favored natural explanations, the very strangeness of Oumuamua highlighted how little we know about the building blocks of other planetary systems. It was a cryptic postcard from a place we will never visit, challenging our assumptions before vanishing forever into the void. Just 2 years later, the universe sent a second, clearer message. In August 2019, amateur astronomer Gennady Borisov spotted another interstellar traveler. This object, named 2I/Borisov, was immediately familiar. It developed a distinct coma and a faint tail as it approached the Sun. This was unambiguously a comet, and its composition, when analyzed spectroscopically, was remarkably similar to comets from our own Oort cloud. It contained cyanogen gas and diatomic carbon, signatures of the icy, primordial material common to our neighborhood. The contrast between the two visitors was illuminating. Oumuamua suggested that other star systems can produce bizarre, unknown object types, perhaps through unique collisional histories. Borisov demonstrated that other systems also create icy planetesimals nearly identical to our own, implying that the processes of planetary formation we see locally might be universal. Together, these fleeting guests revolutionized our perspective. They proved that our solar system is not a sealed bubble. The galaxy is a dynamic ecosystem where stars exchange material, likely through gravitational interactions that fling asteroids and comets into the interstellar deep. This constant traffic has profound implications. In the early days of our solar system, such interstellar vagabonds could have been delivery vehicles, potentially seeding the young Earth with water and complex organic molecules, the very ingredients for life. The detection of these scouts marks the birth of a new field, interstellar object astronomy. It forces us to look at our own celestial backyard with new eyes, recognizing that we are part of a vast, interconnected galactic community. As we learn to spot visitors from other stars, we naturally turn our gaze to the stars themselves, wondering what worlds might permanently orbit them. The interstellar scouts hinted at a universe rich with unseen worlds, a suspicion that became a certainty with a single mission. For millennia, the planets of our solar system were all we knew. The existence of worlds around other stars was a beautiful hypothesis, but the evidence was scant, limited to a few dozen detections of massive, Jupiter-like giants. All of that changed in March 2009, when NASA Kepler Space Telescope began its quiet, relentless stare at a single patch of the Milky Way. Its goal was deceptively simple: to monitor the brightness of over 150,000 stars, looking for the telltale, periodic dimming that occurs when a planet crosses or transits in front of its host star. This transit method is like detecting a gnat flying across a searchlight from thousands of miles away, requiring incredible precision. Kepler delivered it. The flood of data that followed was nothing short of revolutionary. Before Kepler, planets seemed rare. After Kepler, we knew they were everywhere. The mission catalogued thousands of confirmed exoplanets, and its statistical analysis suggests there are more planets in our galaxy than there are stars. Planets are not the cosmic exception, they are the rule. Kepler did more than just count worlds. It revealed a stunning cosmic zoo of planetary diversity that defied our solar system's centric imagination. We discovered super-Earths, rocky worlds larger than our own, and mini-Neptunes, gaseous planets smaller than any in our local neighborhood. We found planets orbiting binary stars like the fictional Tatooine, and planets so close to their suns that years last only hours. Most importantly, Kepler identified numerous planets orbiting within their star's habitable zone, that temperate region where liquid water could theoretically exist on a rocky surface. While this does not guarantee life, it identifies the real estate where the conditions might be right. This statistical census fundamentally rewrote the book on planetary system architecture. Our own orderly arrangement, with small rocky worlds inward and gas giants outward, is just one possible configuration. Kepler showed us systems with giant planets hugging their stars, tightly packed planetary families, and orbits of every conceivable shape. Our solar system is not the standard model. It is simply one variation in a galaxy bursting with planetary possibilities. This profound shift in perspective did more than expand a catalogue. It transformed a philosophical question into a grounded scientific pursuit. The sheer abundance of planets makes the existence of life elsewhere in the cosmos feel not just possible, but statistically probable. It provides a vast field of targets for the next generation of telescopes, like the James Webb, which will begin to analyze the atmospheres of these distant worlds, searching for the chemical fingerprints or biosignatures that might indicate biological activity. The Kepler mission bridged the immense scales of cosmology and the intimate possibility of biology. It connected the galactic processes of star formation directly to the potential for habitable environments, making the search for extraterrestrial life a natural extension of our understanding of cosmic evolution. The mission taught us that while Earth may be unique in its details, the cosmic processes that led to its formation are beautifully, overwhelmingly common. As we ponder the potential for life on distant worlds, we are inevitably drawn to the source of all life's energy, to the very heart of our own planetary system, where a quiet anomaly in the orbit of Mercury once confirmed the most revolutionary idea about the nature of reality itself. The potential for life on distant worlds expands our cosmic perspective, but the most extreme environments remain hidden by their very nature. For a century, the black hole was a powerful mathematical idea, a prediction so absolute it seemed destined to remain invisible. Its defining feature, the event horizon, is a one-way boundary in space-time, a point of no return where gravity becomes so strong that not even light can escape. How could we ever see something that traps all light? The answer was to capture its silhouette against a backdrop of brilliance. In April 2019, the Event Horizon Telescope collaboration unveiled an image that stopped the scientific world in its tracks. It was the first direct visual evidence of a black hole's shadow, a dark central region encircled by a fiery, asymmetric ring of light. This was the supermassive black hole at the heart of the galaxy Messier 87, a behemoth weighing in at 6.5 billion times the mass of our Sun. Creating this image was a feat of staggering global engineering. It required synchronizing a network of 8 radio observatories across 4 continents, from the high deserts of Chile to the volcanic peaks of Hawaii and the frozen landscape of Antarctica. By combining their signals using a technique called very long baseline interferometry, these dishes effectively formed a single Earth-sized telescope. This instrument had a resolution sharp enough to read a newspaper in New York City from a sidewalk cafe in Paris. For several nights in April 2017, every telescope in the array pointed simultaneously at M87. They collected petabytes of raw data that took years to painstakingly calibrate and reconstruct into the now iconic orange ring. The image is a perfect confirmation of Einstein's general relativity under conditions of incredible gravitational force. The bright ring is not the event horizon itself, but superheated gas swirling at near light speed in the accretion disk. The black hole's immense gravity bends the light from this disk, lensing it into a brilliant circle. The dark shadow at the center is the event horizon's silhouette, about 2.5 times larger than the horizon itself. This is a direct manifestation of spacetime's extreme curvature. The ring's asymmetric brightness, brighter on one side, comes from relativistic beaming, where light from gas moving toward us is amplified, while light from receding gas is dimmed. Beyond confirming theory, the image unlocked new understanding of cosmic mechanics. The black hole in M87 is famous for launching a colossal jet of plasma thousands of light years into space. The image orientation suggests this jet is likely perpendicular to the accretion disk. This provides crucial clues about how magnetic fields and spinning black holes can power these universe-spanning beams. It gave us a direct view of the chaotic, energetic environment where gravity dominates everything, from the flow of matter to the very path of light. This was more than a scientific first, it was a profound cultural moment. It transformed an abstract mathematical singularity into a tangible cosmic object, a place we could point to and say, there it is. It demonstrated the power of human collaboration on a planetary scale, turning our world into a single instrument of discovery. Seeing the unseeable did not just validate a century of theoretical work, it opened a new window. It proved we could directly image and study the most extreme gravitational environments in the universe. This gave us the confidence to probe for even subtler ripples in the fabric of reality, where our understanding of gravity itself might begin to evolve. A profound silence followed the detection of the WOW signal. On the evening of August 15, 1977, astronomer Jerry Amon was reviewing a computer printout from the Big Ear radio telescope at Ohio State University. The telescope was part of a quiet, systematic search, scanning the sky for any narrowband radio signal that might stand out against the cosmic background noise. Amon's eyes scanned the columns of alphanumeric data, a routine check of the universe's static. Then he saw it, a sequence of characters indicating a signal so strong, so precisely tuned that it leapt off the page. In the margin, he circled the code and wrote a single, emphatic word. Wow! The signal, detected in the constellation Sagittarius, lasted for the telescope's full 72-second observation window. It was narrowband, meaning it was focused on one specific frequency, a hallmark of engineered communication rather than the broad, messy emissions of natural astrophysical processes. It matched the expected profile of an interstellar transmission perfectly, and then it vanished. Despite repeated and determined attempts to find it again, the signal never returned. It was a one-time event, a cosmic whisper that arrived, made its mark, and disappeared into the void. The mystery of its origin has endured for decades. Was it a message, a fleeting beacon from an intelligence beyond our world? Or was it a remarkable but natural astrophysical event, perhaps an unknown form of stellar emission or a signal reflected off a piece of space debris? The most likely natural explanation points to a comet, though this too is debated and does not fully satisfy all the data. The truth is, we may never know. Yet the power of the WOW signal lies not in its resolution, but in its profound ambiguity. It became a cultural touchstone, the most famous candidate for a signal we cannot explain. It transformed the search for extraterrestrial intelligence, or SETI, from a speculative fringe idea into a serious scientific endeavor with a tangible, haunting question mark at its center. It underscored the immense challenge of the search. The cosmos is a cacophony of natural radio noise, from the faint hiss of the cosmic microwave background to the powerful pulses of distant pulsars. Finding an artificial signal is like listening for a single, distinct voice in a roaring stadium. The WOW signal demonstrated that a candidate could appear, matching every criterion, and still remain forever unverified. It taught the necessity of repeatability, of verification from a second telescope, a lesson that now defines all modern SETI protocols. This single event redefined public engagement with humanity's oldest cosmic question. Are we alone? The WOW signal did not answer it, but it made the question feel urgent, real, and scientific. It inspired a generation of researchers to build more sensitive instruments and develop smarter algorithms to sift through the cosmic noise. It reminds us that the ultimate astrophysical event, first contact, would not be a discovery in a single field. It would instantly shatter and remake our understanding of cosmology, biology, and philosophy. It would tell us that the processes that led to us are not unique, that the universe is not just a physical place, but a potential community. The search continues, listening patiently to the stars, knowing that the next wow could be the one that changes everything. And as we listen for voices in the cosmic dark, we must also learn to interpret the universe's own, more intense language, written in the most energetic light it can produce. The search for a cosmic voice requires listening for the most precise rhythms the universe can offer. In the quiet English countryside of 1967, a young doctoral student named Jocelyn Bell Burnell was reviewing miles of chart paper from a new radio telescope she had helped build. Her task was to analyze the data for the subtle twinkling of distant quasars, but her eye caught something else entirely. A faint, rhythmic pulse, a signal so regular it seemed almost artificial. It appeared and reappeared every 1.337 seconds with a precision rivaling the best atomic clocks on Earth. This was no human transmission. The source, designated CP1919, was the first recognized pulsar, a cosmic lighthouse whose discovery would illuminate one of the most exotic transitions in stellar life. The scientific community was initially baffled. The signal's extreme regularity led to brief, serious speculation about an artificial source, humorously labeled LGM for little green men. But Jocelyn Bell Burnell's diligence soon revealed more of these pulsing sources across the sky, ruling out an intelligent origin. The true explanation was even more astonishing. Theorists realized these were rapidly spinning neutron stars, the ultra-dense cores left behind when massive stars reach their spectacular conclusion. A neutron star packs more mass than our Sun into a sphere just the size of a city. Its magnetic field, trillions of times stronger than Earth's, channels radiation into narrow beams from its magnetic poles. If these poles are misaligned with the star's rotation axis, the beams sweep across space like the beacon of a lighthouse. Each time a beam sweeps across Earth, we detect a pulse of radio waves. This discovery was monumental. It provided the first direct observational evidence for neutron stars, a theoretical prediction that had lingered for decades. It confirmed a crucial link in the stellar life cycle, showing that a star's final act could leave behind an object even more fascinating than the star itself. Pulsars became nature's most exquisite natural laboratories. Their incredible density, where a teaspoon of material would weigh billions of tons, allows us to study states of matter impossible to replicate on Earth. Their intense gravity provides a perfect arena for testing Einstein's theory of general relativity with unmatched precision. The usefulness of these cosmic metronomes was proven spectacularly with the discovery of the binary pulsar PSRB 1913 plus 16 by Russell Hulse and Joseph Taylor in 1974. This system consists of two neutron stars orbiting each other. By meticulously timing the pulses from one of them, astronomers could track its orbit with phenomenal accuracy. They found the orbit was decaying, the two stars spiraling inward by exactly the amount predicted if they were losing energy by emitting gravitational waves. This was the first indirect but compelling evidence for the existence of these spacetime ripples, a discovery that would earn a Nobel Prize and pave the way for direct detectors like LIGO decades later. Beyond testing gravity, pulsars serve as tools for galactic exploration. As their pulses travel across thousands of light years, they pass through the interstellar medium. This subtly delays different radio frequencies, allowing astronomers to map the distribution and magnetic field of the thin gas between the stars. Their legendary timing stability has even inspired proposals to use networks of pulsars as a galactic positioning system, a potential navigation aid for future spacecraft traveling between the stars. Jocelyn Bell Burnell's careful attention to a curious signal redefined our view of stellar legacy. She showed that a star's story does not simply conclude, but transforms into a precise and powerful tool. Pulsars are the steady, ticking hearts of ancient stellar events, their gradual slowdown telling the story of their energetic youth. They remind us that the universe is filled with clocks of unimaginable scale, keeping time to a rhythm set by gravity and spin. As we learned to read these clocks, we also began to notice a different kind of signal, one that suggested entire galaxies could be synchronized by a force far more ancient and vast than any single star. The precise ticking of pulsars gave us a rhythm for the cosmos, but some signals arrive with no warning at all. In 2007, a new kind of cosmic flash entered the astronomical record, a burst of radio waves so intense it outshone entire galaxies for a few milliseconds. These were fast radio bursts, mysterious events that appeared to be singular cataclysms, vanishing as quickly as they arrived. Their origin was a complete enigma, sparking theories ranging from evaporating black holes to advanced cosmic engineering. Then, in 2016, a breakthrough observation changed the game entirely. Astronomers discovered that one source, catalogued as FRB 121102, was repeating. It was not a single destructive event. It flashed again and again and again. This simple fact that the signal repeated was a monumental clue. It meant the source had to endure its own outburst, ruling out any model that involved the total annihilation of the object. The repeater offered a precious opportunity. Because it kept flashing, astronomers could point the world's most powerful radio telescopes, like the Arecibo Observatory and the Very Large Array, at its location with patience and precision. They succeeded in triangulating its position with astonishing accuracy, tracing it back not to a random point in the void, but to a small, faint dwarf galaxy 3 billion light-years away. This was the first time a fast radio burst had ever been given a cosmic address. Pinpointing the host galaxy was like finding the neighborhood of a mysterious lighthouse. Studying this dwarf galaxy revealed it was a place of intense stellar formation, a turbulent nursery where massive stars live fast and leave behind exotic remnants. This environmental clue, combined with the repeating nature of the bursts, strongly pointed to a specific type of stellar remnant as the culprit, a magnetar. Imagine a neutron star, but with a magnetic field 1,000 trillion times stronger than Earth's. These magnetars are cosmic magnets of unimaginable power, and theorists suggest that starquakes on their surfaces or interactions with surrounding material could unleash the colossal, focused energy of a fast radio burst. The repeating bursts from FRB 121102 suggested a source that could build up and release energy multiple times, perfectly fitting the magnetar model. But the scientific value of these flashes extends far beyond identifying their source. As a fast radio burst travels across billions of light-years of intergalactic space, its signal gets stretched. Different radio frequencies arrive at slightly different times. This dispersion is caused by free electrons floating in the vast, diffuse plasma that fills the space between galaxies, the very material that makes up the cosmic web. By measuring how much the burst signal has been spread out, astronomers can count the number of electrons it passed through. This allows them to weigh the invisible, hot gas that theorists knew must exist but had been nearly impossible to detect. In this way, fast radio bursts have become cosmic measuring tools. Each one that we detect and localize gives us a single, precise measurement of the amount of diffuse matter along its specific path through the universe. They are helping us solve the mystery of the missing baryons, the ordinary matter that our inventories of stars and galaxies could not account for. It appears this matter is indeed out there, in the form of a thin, hot fog tracing the filaments of the cosmic web. From profound mysteries, these bursts are being transformed into powerful new tools. They are probes of the most extreme magnetic fields in the universe, and now maps of the universe's hidden material skeleton. Each flash is a momentary illumination, not just of its source, but of everything between it and us. The Sun, our nearest star, was hiding a secret in its core. For decades, scientists had built exquisite detectors deep underground, shielded from cosmic rays, to catch the ghostly neutrinos produced by the nuclear fusion that powers our star. These particles, nearly massless and barely interacting with matter, should have streamed directly from the solar core to our detectors, offering a real-time probe of the Sun's inner engine. Yet the numbers did not add up. From the 1960s onward, experiment after experiment, like the pioneering Homestake mine detector, consistently found only about 1/3 of the predicted flux of electron neutrinos. This glaring discrepancy was the solar neutrino problem, a quiet crisis that persisted for over 30 years. It presented a troubling choice. Either our detailed, elegant models of how the Sun shines were fundamentally wrong, or something strange was happening to the particles on their 8-minute journey to Earth. The resolution, when it finally came, was more profound than anyone had imagined. It was not our understanding of the Sun that was flawed, but our understanding of the particles themselves. The key was a phenomenon called neutrino oscillation. Theorists had proposed that if neutrinos had even a tiny amount of mass, they could change identity or flavor as they traveled through space. An electron neutrino born in the solar core could transform into a muon or tau neutrino by the time it reached Earth. Since the early detectors were only sensitive to electron neutrinos, they were missing 2/3 of the total signal. The neutrinos were not missing, they were simply in disguise. Proving this required a new generation of detectors capable of seeing the full picture. In the late 1990s and early 2000s, experiments like Supermassive and in Japan and the Sudbury Neutrino Observatory in Canada provided definitive proof. The Sudbury experiment was particularly elegant, using heavy water to detect all 3 neutrino flavors simultaneously. Its data showed conclusively that the total number of neutrinos arriving from the Sun matched theoretical predictions perfectly. The missing neutrinos had been found, having changed into other types along the way. This discovery was a monumental triumph on multiple fronts. First, it resoundingly validated our models of stellar processes. The Sun was working exactly as we thought, a triumph for astrophysics. But second, and more revolutionary, it forced a change in the fundamental laws of particle physics. The Standard Model, our most successful theory of subatomic particles, had long assumed neutrinos were massless. The fact that they oscillate proves they must have mass, however infinitesimal. This was the first clear, experimental evidence that the Standard Model is incomplete, a signpost pointing toward new, deeper physics. The implications ripple outward from the solar core to the entire cosmos. Neutrinos are among the most abundant particles in the universe, relics from the earliest moments. The fact that they have mass means they contribute to the overall fabric of the cosmos, influencing the growth of large-scale structures and the ultimate fate of the universe. The solution to the solar neutrino problem stands as a beautiful example of cosmic synergy. We used a star as a laboratory to uncover a fundamental truth about the building blocks of reality. It demonstrated that the universe's largest objects and its smallest particles are inextricably linked, and that sometimes the answers to our biggest questions arrive on the faintest, most ghostly signals from the heart of a star. Having now confirmed the inner workings of our own Sun, we turn our detectors toward neutrinos born in far more energetic cosmic events, where they carry stories of creation from the edge of spacetime itself. Ghostly particles from our Sun solved one mystery, but they carry whispers from a far greater chorus. Every second, trillions of neutrinos pass through your body, and a tiny fraction of them come from beyond our solar system. Some are relics from the very first second of the universe, but others tell a more recent and powerful story. They are the faint echoes of stellar transformations happening across the cosmos. For decades, we have detected neutrinos from our own sun and captured a precious burst from a single, nearby stellar event. But the ultimate goal is far more ambitious: to hear the combined, ancient hum from every massive star that has ever reached its spectacular conclusion. This is the hunt for the diffuse supernova neutrino background. Imagine the universe as a vast, dark forest. A single, brilliant flash is like a supernova in our own galactic neighborhood, impossible to miss. But if you could hear instead of see, you might perceive something else: a constant, gentle rustling made by the leaves of every tree in that forest, all at once. That rustle is the diffuse supernova neutrino background. It is the integrated signal, the combined neutrino output, from every core collapse supernova that has ever occurred in the observable universe, stretched across 13.8 billion years of cosmic history. These particles have been traveling since the first generations of massive stars began their final transitions, and they now permeate all of space like a sea of silent witnesses. Detecting this background is one of the great challenges in modern physics, because the signal is incredibly faint, drowned out by neutrinos from our sun, from cosmic rays interacting with our atmosphere, and even from natural radioactivity in the rocks around our detectors. It is like trying to hear a single conversation in a roaring stadium, but next-generation observatories are being built for this exact purpose. Projects like Hyper-Kamiok and in Japan and the Deep Underground Neutrino Experiment in the United States will use colossal volumes of ultra-pure water and exquisite light sensors placed deep underground to shield from interference. Their unprecedented scale and sensitivity are designed to finally pick this cosmic whisper out of the noise. Why is this hum so important? Because it represents a cosmic census conducted in a completely new language. All our knowledge of the universe's star formation history comes from light. We look at galaxies and measure their brightness, their colors, their rates of producing new stars. But light can be obscured by dust, it can be misleading, and it only shows us what is happening now in those distant galaxies, not what happened billions of years ago. The diffuse supernova neutrino background offers an independent, integral measure. It does not count individual stars, it sums them all up. By detecting the energy spectrum and the flux of these ancient neutrinos, scientists can calculate the total number of massive stars that have ever completed their life cycles. This provides a direct, unobscured check on our theories of cosmic chemical evolution, telling us if our picture of how many stars lived across time is correct. It will also open a unique window into the supernova process itself. The neutrinos carry information about the conditions inside the transforming stellar core, the very engine of the explosion. By studying this background, we gain an averaged view of how stars across all of cosmic history have reached their final stages. This discovery will do more than add another data point. It will weave a new thread into the fabric of cosmology. It connects the specific chirps of gravitational waves from nearby mergers to the universal sigh from all stellar conclusions. It will solidify the role of the neutrino not just as a subatomic particle, but as an essential cosmic messenger, one that carries unfiltered news from the most energetic, creative events across the entirety of time and space. To hear this hum will be to listen to the universe's own heartbeat, a slow, steady rhythm of creation forged from transformation. That cosmic hum of ancient neutrinos is a whisper from the integrated past, but to understand the universe's first moment, we needed a perfect snapshot. Between 2009 and 2013, the European Space Agency's Planck satellite performed a quiet, meticulous survey of the entire sky. Its mission was to look back not with a telescope for stars, but with a radiometer for cold, ancient light. It mapped the cosmic microwave background, the afterglow of the beginning, with a sensitivity and resolution that was nothing short of revolutionary. The image it produced was not just a prettier version of what came before. It was the ultimate baby picture of the cosmos, taken when the universe was a mere 380,000 years old, rendered in exquisite scientific detail. Every subtle variation in temperature, every faint pattern in the polarization of that light, was a data point, a piece of a cosmic code. Planck's instruments were so sensitive they could measure temperature differences of a few millionths of a degree. This precision allowed scientists to perform what amounted to a cosmic audit. By analyzing the statistical patterns in that ancient light, the Planck team could calculate the universe's fundamental recipe with astonishing accuracy. The results gave us our modern, numerically precise cosmology. The universe, they found, is composed of about 5% ordinary matter, the atoms that make up stars, planets, and us. About 27% is dark matter, the invisible gravitational glue that holds galaxies together, and a dominant 68% is dark energy, the mysterious force accelerating the expansion of space itself. This is the lambda-cold dark matter model, the standard framework of our universe, quantified and confirmed. The mission did more than just weigh the cosmos. It measured its age with unprecedented confidence, pinning it at 13.8 billion years. It confirmed with overwhelming evidence that the geometry of the observable universe is flat, meaning parallel lines will never meet on cosmic scales, a key prediction of inflation. Planck also scrutinized the subtle swirly patterns, called B-mode polarization, in the ancient light. While it did not find the definitive signature of primordial gravitational waves from inflation, its measurements placed incredibly tight constraints on inflationary models, narrowing down the vast landscape of possible theories about that first instant. Planck's legacy is a universe understood with numbers of breathtaking precision. It turned the faint afterglow of creation into the most rigorous laboratory we have, a reference point against which every new theory and every puzzling anomaly must be tested. It solidified our standard model of cosmology, a triumph of human curiosity and engineering. Yet, in doing so, it also cemented our awareness of the unknown. By so precisely quantifying the 68% dark energy and the 27% dark matter, it highlighted that 95% of the universe is made of substances whose nature remains a profound mystery. Planck gave us a complete and precise map of the cosmic terrain, while simultaneously pointing to vast, uncharted territories that lie beyond its edges. Its data is the bedrock, the high watermark of classical cosmology, against which the persistent tide of the Hubble tension now laps, suggesting that even our most perfect map might need a new legend. That precise cosmic map from Planck highlights the profound unknowns in our universe's recipe, particularly the true nature of dark matter. While many candidates are exotic new particles, one possibility is both ancient and familiar, a relic from the universe's first chaotic moments. These are primordial black holes. Unlike the stellar mass black holes born from collapsing stars or the supermassive giants at galactic centers, primordial black holes are thought to have formed directly from the extreme density of the infant cosmos. In the first second after the beginning, when everything was a seething, ultra-dense soup, random quantum fluctuations could have created pockets so dense they collapsed directly under their own gravity. This makes them a potential direct product of cosmic inflation, a tangible fossil from an era we can never directly observe. Their predicted masses are as varied as their origin is profound. They could be as light as a small asteroid or as heavy as thousands of suns, with every possible size in between. This incredible range opens a fascinating possibility. Could some, or even all, of the universe's missing dark matter be made of these ancient, invisible objects? If a significant portion were composed of asteroid mass primordial black holes, they would be everywhere, drifting unseen through galactic halos, including our own. We would not notice them unless they passed directly between us and a distant star. In that rare alignment, their gravity would act as a lens, briefly bending and magnifying the star's light in a telltale flash known as microlensing. Astronomers have conducted extensive surveys monitoring millions of stars for these fleeting brightenings. So far, the number of observed events suggests that while some primordial black holes might exist, they cannot account for all the dark matter, at least not in the most commonly searched mass ranges. The search has expanded into new frontiers. The gravitational wave observatories LIGO and Virgo listen for the mergers of black holes. Some of the pairs they have detected fall into a mass range that is puzzling for traditional stellar evolution, reigniting interest in a primordial origin. Could these be ancient black holes formed in the early universe, now finding each other in the cosmic dark? Furthermore, the subtle ways these objects would influence the delicate patterns in the cosmic microwave background or shape the formation of the very first stars provide additional observational tests. Each result that does not find them helps rule out specific mass windows, narrowing the hunt. The ongoing quest is a perfect example of cosmology's bold ingenuity. It takes a theoretical possibility born from our understanding of the universe's first instant and devises multiple, independent ways to hunt for its fingerprints across the entire history of the cosmos. Their discovery would be a double revolution. First, it would solve the dark matter puzzle with objects predicted by Einstein's theory, rather than requiring entirely new physics. Second, and perhaps more profoundly, it would give us a direct physical link to the era of inflation. We would hold in our observational grasp an object that formed directly from the quantum seeds of everything, a singular relic from the universe's very first breath. This search reminds us that the answers to our greatest cosmic questions might not be found in undiscovered particles, but in ancient shadows we have only just learned how to see. Ancient shadows from the first instant hint at a reality far stranger than a single cosmos. Our journey through 30 events has brought us to the very edge of what we can observe, and here, theory paints a picture that redefines the meaning of everything. This is not a 30th event in the traditional sense, for there is no telescope data, no sudden flash in the sky to point to. It is an idea, a profound implication drawn from the sum of all we have learned. It is the concept of a multiverse. This notion emerges almost inevitably from our most successful theories. Take cosmic inflation, the idea that our universe underwent a period of exponential expansion. Some versions of this theory suggest this expansion may be eternal, never truly stopping. In this model, the inflating energy of space can settle in some regions, creating pocket universes like ours, while inflation continues forever elsewhere. Each pocket becomes its own separate cosmos, with its own beginning and its own subsequent history. According to this eternal inflation, our universe is just one bubble in a frothing, infinite sea of universes, a cosmic foam where new realities are constantly budding into existence. String theory, a leading candidate to unify all forces of nature, adds another dimension to this picture. To be mathematically consistent, it requires more spatial dimensions than the three we experience. It also suggests a staggering number of possible stable configurations for those extra dimensions, perhaps 10 to the 500 or more. Each configuration would result in a different set of physical laws and constants for its corresponding universe. In this string theory landscape, our universe, with its specific charge of the electron and strength of gravity, is just one possible outcome among a number so vast it defies human comprehension. Why does this speculative idea carry such weight in modern cosmology? Because it offers a potential, if controversial, answer to the most haunting question raised by our discoveries, the problem of fine-tuning. Our universe appears exquisitely balanced for complexity and life. The cosmological constant, the value of dark energy, is precisely calibrated. If it were slightly larger, the universe would have blown apart before stars could form. If it were slightly smaller, gravity would have caused a rapid collapse. The strengths of the fundamental forces, the masses of particles, all seem set within razor-thin margins that allow atoms, chemistry, and ultimately us to exist. The multiverse concept provides a possible framework for this. If there are an infinite number of universes, each with randomly different constants, then it is no surprise that we find ourselves in one of the rare habitable ones. We are, in a sense, a cosmic selection effect. This idea forces a fundamental re-evaluation of the scientific process itself. By its nature, the multiverse may lie permanently beyond our observational horizon, as other pocket universes would be causally disconnected from our own. This raises a profound philosophical challenge. If a theory predicts an infinite number of universes we can never see or interact with, is it still science? This debate sits at the frontier of cosmology, pushing at the very definition of what it means to explain something. It compels scientists to search for indirect signatures within our own cosmos, perhaps imprinted on the cosmic microwave background from an encounter with another region in the distant past, or through subtle effects on the large-scale structure of space. The multiverse represents the ultimate horizon of our story. It is where the chain of cause and effect, traced back from a supernova's light or a gravitational wave's chirp, leads to a dizzying possibility. Our universe, with all its brilliant events and silent mysteries, may be a single chapter in a library of cosmic histories, so vast its full text may forever be unreadable. This speculative leap does not diminish our discoveries, it expands their context to an almost unimaginable scale. It suggests that every event we have chronicled, from the first silent flash to the acceleration of space, is part of a local narrative within a much grander, and perhaps eternal, meta-story. Our search for understanding began by looking up at the stars, and it has led us to contemplate the nature of reality itself. These threads are not separate stories, but a single, woven tapestry. From the faint hiss of the cosmic microwave background to the faint chirp of colliding black holes, each discovery is a stitch in a grand, coherent narrative of cosmic evolution. This tapestry reveals a universe that is profoundly dynamic, a system in constant motion from its first instant to its accelerating future. It is governed by a beautiful, elegant set of physical laws we have come to understand, yet it is dominated by components, dark matter and dark energy, whose fundamental nature remains one of science's greatest puzzles. This is the central paradox of modern cosmology, a field that knows the universe's history and destiny with stunning precision, yet does not know what 95% of it actually is. The journey through these events is a story of cumulative understanding where each breakthrough did not stand alone. The discovery of the expanding universe set the stage for the prediction of the cosmic microwave background. The mapping of that ancient light gave us the seeds for the cosmic web, which in turn explained the environment where galaxies could form and evolve. The precise measurement of supernova revealed dark energy, which then prompted us to re-examine the very first moments through the lens of inflation. This is not a chain of isolated facts, but an interconnected web of cause and effect, where answering one question inevitably leads to a deeper, more profound one. Underpinning this entire narrative is the engine of human ingenuity. Each leap in understanding was enabled by a corresponding leap in technology. The radio antenna that heard the Big Bang's echo, the space telescope that peered back to the cosmic dawn, the laser interferometer that felt the fabric of spacetime ripple, these are the tools that extended our senses. They transformed cosmology from a branch of philosophy into a rigorous, predictive science. We moved from wondering about the stars to weighing the universe, from speculating about beginnings to calculating its age to within a 1% margin of error. This means cosmology is a living, breathing science. It is not a set of facts carved in stone, but a story being written and rewritten with each new observation. The greatest inquiries of today, like the persistent Hubble tension or the elusive identity of dark matter, are not shortcomings. They are the vital signs of a healthy, thriving field. They are the unresolved chords in the symphony, the gaps in the map that draw explorers forward. They remind us that our standard model, for all its success, is a stepping stone, not a final destination. Ultimately, this tapestry is a human achievement. It is a testament to our species' relentless curiosity and our collaborative drive to make sense of our place in the vastness. We have taken the faintest whispers from the void, a redshifted galaxy, a distorted image, a stream of ghostly particles, and from them woven a complete history of the cosmos, from a hot, dense beginning to a cold, dark future. We have mapped our origin and predicted our destiny, all while humbly acknowledging that most of the universe is still hidden from view. The story of modern cosmology is the story of us, reaching out into the darkness with light and reason, slowly pulling back the veil to reveal a reality more wondrous and strange than we ever dreamed. This grand tapestry of discovery is not a finished work, but a living document written in the light of ancient stars and the whispers of empty space. These 30 events are far more than historical footnotes. They are the very foundation of our current cosmic understanding and the essential launchpad for every future discovery. They teach us a humbling and exhilarating lesson that the universe is fundamentally a place of surprise, capable of overturning our deepest assumptions with a single, faint signal from the void. The redefinition of cosmology is not a process that happened once. It is an ongoing, vital conversation, driven by the creative tension between our elegant established models and the stubborn, anomalous data that refuses to fit. This is where science becomes most alive. It is in the quiet persistence of a discrepancy like the Hubble tension, or in the decades-long search for a particle we cannot see. The entire history we have traced is a story of questions leading to answers, which in turn lead to deeper, more profound questions. So what will the next redefining event be? Perhaps it will be the direct, unambiguous detection of a dark matter particle in a deep underground laboratory, finally giving a name to the cosmic framework. It might be a revolutionary insight into the nature of dark energy, revealing it to be a dynamic force that changes over time, reshaping our vision of the cosmic future. Or it could be the discovery we have dreamed of for millennia, a definitive biosignature in the atmosphere of a distant exoplanet, telling us we are not alone in the great cosmic story. The cosmos continues to extend an open invitation to curiosity. It asks us to keep looking with ever more sensitive eyes, to keep questioning even our most cherished theories, and to keep exploring the boundaries of the knowable. If this journey through the events that shaped our universe has sparked your curiosity, we would love to hear from you. Share your thoughts in the comments below about which discovery you find most astonishing or which mystery you hope will be solved next. And if you want to join us as we cover the next great revelation, the one that will once again redefine our place in the universe, be sure to subscribe and hit the notification bell. The next chapter is being written right now, in the data streams of telescopes and the quiet hum of detectors, waiting for its moment to change everything.